Projection matrices. In this lesson, we discuss orthogonal projection matrices, which like orthogonal matrices frequently arise in application. A projection matrix has a simple geometric interpretation. Let's use this glass Earth to demonstrate. The Earth lives in three-dimensional space. Consider a plane which is a two-dimensional subspace of our three-dimensional space. Except for a disk, the Earth lives completely outside the plane. But, this plane has an orthogonal projection matrix associated with it. The projection matrix squashes the Earth completely and orthogonally into the plane. All three-dimensional information about the Earth is discarded. Antarctica is now neighboring California, and it is impossible to undo this process. There is no information which tells us from where the points came. We'll start by looking at the projection onto a line. Suppose two vectors v and w subtend an angle theta. The projection of the vector w onto the line spanned by the vector v is simply the component of w in the v-hat direction. Let's rewrite this expression without the explicit theta dependence. Recall that the dot product of two vectors is the product of the length of the two vectors times cosine theta. By dividing through by the norm of v, we have the norm of w times cosine theta on the right-hand side. This is exactly what we need. Let's substitute the left-hand side into our expression for the projection. Okay. Now we have that the projection of w onto v is simply v transpose w divided by the norm of v, times v-hat. We can simplify the right-hand side a little bit more to get it to be an operator acting on the vector w. Let's replace v-hat with v divided by the norm of v. Now, we'll multiply the two ratios together. Because v transpose w is a scalar, we can move it after the v in the numerator. Now, we'll grab w, and push it off of the ratio, so that we have an operator acting on w. This operator is the projection operator for the line spanned by the vector v. If we apply it to any vector, that vector will be squashed onto the line in the direction of v-hat. Any component orthogonal to the line will be zeroed out. We can furthermore expand the denominator into v transpose v. Then we have an outer product divided by an inner product. For vectors in n-dimensional space, P is an n by n matrix. As an example, let's find the projection matrix from R3, onto a line spanned by the vector v equals 2, 1, 3. The projection matrix is given by v transpose divided by v transpose v. We substitute in the value for v, and then multiply the terms together. Let's generalize the discussion from an orthogonal projection matrix of a line to that of an arbitrary subspace. A plane, a hyperplane, or whatever. Let A be an m by n matrix whose columns span a given subspace. We want the projection matrix to have two properties. It does not change any vector that is already in the subspace spanned by the columns of A, and it zeroes out any vector that is orthogonal to the subspace spanned by the columns of A. We'll skip the derivation and just show that the matrix A, times A transpose inverse, times A transpose, satisfies these requirements. To show that the first requirement holds, we apply the projection operator to A. The term A transpose A cancels with its inverse, and we are left with A. To show the second requirement, we apply the projection operator to B. Since A and B are orthogonal, A transpose times B equals 0. And we are left with 0. Let's look at some of the other properties of an orthogonal projection matrix. P squared equals P. Once a vector has been projected into a subspace, applying the projection matrix a second time doesn't do anything. P transpose equals P. The projection operator is symmetric. This ensures that the projection is orthogonal. The rank of P equals the rank of A. From this it follows, if A is an invertible operator, then P equals the identity operator. Let's look at a practical application of the projection matrix. We would like to find the equation for a parabola which passes through the points 0, 1, 1, 1, 2, 0, and 3, 3. We can write this problem as a linear system using a Vandermonde matrix. The system is overdetermined and has no solution. This is because the vector b is not in the column space of A. We'll use a projection matrix to put it there. We multiply p on both sides of the equation. On the left-hand side, we have that p times A equals A. On the right-hand side, we write out the projection matrix explicitly. We can simplify the right-hand side by multiplying both sides by A transpose. This allows us to cancel some terms. We get the so-called normal equations A transpose A times x equals A transpose times b. We replace x with x tilde to denote that we are not actually solving the original system, but instead a modified system. The solution of this system is called the least square solution. It is called this because it is the solution that minimizes the error in the Euclidean norm. Now, let's apply the normal equations to the original problem ax equals b. We multiply both sides of the equations by A transpose to set the normal equations. The solution to the normal equations gives us the least square solution. We have that the best fit parabola is y equals 3/4 x squared minus 7/4 x plus 5/4. The solution worked by projecting the problem into the subspace of quadratic polynomials. We then solve the new system to pick the parabola that passes through the projected points.